So we have seen simplex method. We'll see exceptional cases. Exceptional cases. See, when we were solving LPP by simplex method, there are two possibilities where we have to choose between two similar quantities. What are they? First is the tie between two incoming variables. See, when will you have this tie? When when two or more CJs are equal. See, here what we do, Cj, that is Zj minus small cj. We calculate it, and what we choose? We choose the value of Cj which is maximum positive. What if two of them or more than two have same value? Then which should be the incoming case? We simply choose the maximum positive value of Cj, and that is our key column, and the variable that forms that column, we make it the incoming variable. But if we have, let's say, two Cjs of same value, both are 8 and 8, and one is x1 and second is x2, then which one should be the incoming variable? This is the issue. This is the first exceptional case. Here you don't have to worry much. What you need to do is you choose any of the variable. Choose any variable. Choose any variable as incoming. Okay, you can choose anyone arbitrarily. Whichever pleases you, you can choose. You don't have any issue. Now, the second one. The second one is tie between two outgoing variables. Now, how do we decide which is our outgoing variable? We take theta, which is the ratio of b by the element of the key column. If two values of theta are same, then which one should be taken? See, if the value is greater than 1, you can choose anyone. You can choose anyone. Whichever suits you, you can choose. That is, if the value of theta is 3 and 3, you can choose anyone. But if the value of theta is 0, particularly 0, then it becomes difficult to choose. Then what to do? We use degeneracy to choose which row to make key row. Okay, we'll discuss degeneracy in our next segment. Okay, so what is degeneracy? Degenerate. When is the solution degenerate? When any of the basic feasible variable becomes 0. That is degenerate. The issue is in degeneracy, what we have generacy. The problem is that sometimes when you choose an outgoing variable, the process becomes cyclic. That is, every time you keep on entering a new variable, that is an incoming variable, and exiting this from column basis column. So incoming, outgoing, this keeps on repeating without getting any optimal result. The process becomes cyclic. So what we do, we use perturbation technique. See what it is. I'll take an example and then explain to you properly. But for the time being, you should understand that if theta is same for two, theta 1 and theta 2, then what you'll do, if you have S1, S2, S3, three variables, this will be like this, 0, 0, 1 and 1, sorry, 0, 0, 1, sorry, this. So what you do, if your x3 is the key column, let's say 2, 3, 4, if this was your key column, then this column, first S1 column, you divide by the elements of this column, that is 1 by 2, 0 by 3, and okay, theta and theta 1 was, so this and this was same, this and this. We had to decide which one to choose when theta 1 is equal to theta 2. This is 1 by 2, this is 0 by 3. The lower ratio will be 0, this is half, this is 0. So the lower ratio will be our key row. So we'll take this as key row instead of this. This will get out of that cyclic issue. Okay, so this is the exceptional case, how we handle it. So I'll take an example and then we'll understand this. So let's see a very simple example where we use the concept of degeneracy. That is, we'll have two ratios theta equal, and we'll have to decide which one to take as key row. So let's, first of all, what we do, we take slack variables for x1 plus x2, let's say s1, and for second s2 equal to 8. This is our first constraint. 2x1 plus x2 plus 0 into S1 plus S2 equal to 4. So this is our second constraint. So 4x1 plus x2 plus S1 plus 0 S2 equal to 8. This is the first constraint. This is 2x1 plus x2 plus 0 S1 plus S2 equal to 4. This is the second constraint. This is 0 S1, 0 S2. So we have written this in standard form. S1, S2, X1, X2 are greater than equal to 0. So our question, our LPP linear programming problem is now presented in standard form. Now we will start with the creation of the initial basic feasible solution. So we have two constraints, and for this n equal to 4 and m is 2, so we'll have two basic variables and two non-basic variables. So let's start with this. We'll have CB here, this will be basis, and then we'll have x1, x2, s1, s2, b. Okay, so we'll start with s1 and s2 as basic variables as we do, and we'll put x1 and x2 equal to 0. Now the coefficient of these variables in the objective function is 0 and 0, x1, x2. So first constraint 4 and 1. See, 4, 1, 1, 0. The second is 2, 2, 1, 0, 1. B is 8 and 4. Okay. Our Cj, small cj is 9300, 9300. And let's compute Zj. This is this into this plus this into this. So this is 0, 0, 0, 0. Why? Because this is 0, 0. So whichever multiplication we'll take will be 0. So Cj will be this small cj minus Zj. So 9 minus 0, 9, 3 minus 0, 3, 0, 0. Okay. Now this is largest value 9. So this is our key column. We'll have to see which is our key row. See how we find the key row. Now first of all we'll take theta. So how we find theta? Theta is b by coefficient of the first column. So 8 by 4, this is 2. 4 by 2, this is 2. See, this is the issue that we were talking of, that we get the same ratio. Then which one to decide? You can arbitrarily decide any one, but a better way is to do what is called perturbation process. So what we do? We divide throughout by the key element, that is not the key element, by the coefficient of the first this column, key column. So when you divide it in the unit matrix, this will be 1 by 4 and this will be 0 by 2. So this is 1 by 4, this is 0. Which is less? This is less. So what we'll do? We'll decide this as key row. Clear? We were doing this in our simplex method up till now, and we were choosing this arbitrarily. But I told you, if you choose arbitrarily, your process may be cumbersome. The process may become cyclic. That is, one will go and another will come. This will keep replacing. So what we need to do is, we'll divide this by the first column element, not first column, key column element, and in this unit matrix, this is your unit matrix. So whichever is less, we'll choose that row. So this is 0, so we'll choose this row. Okay. So this is our key row and this is our key column. So our key element is this. Clear? So the incoming variable is x1 and outgoing variable is s2. Clear? So what we do? We bring this here, x1, and along with this we bring its coefficient 9. We have to make this 1. We have to make this unity. So what we do? We divide throughout by 2. So when you divide this by 2, you will get 1. This will be 1 by 2, 0 by 2, no issue, 1 by 2, and this is now 2. Okay. Okay. Then second thing what we do is, we make other elements of key column 0. So what we'll do? Row 1, this is row 1. So row 1 minus 4 of row 2. If you do row 1 minus 4 of row 2, this will be 0. So row minus 4 of this, 0. 1 minus 4 of this. See, 4 into half is 2. So 1 minus 2 is minus 1. 1 minus, so nothing. 0 minus 4 of this. So this is minus 2. And 8 minus 4 of this. So this is 0. Okay. So we have done our job till now. Now we have to find Zj and then Cj. Zj will be this into this plus this into this. So this will be 9. Okay. So this is 9 and this is 0, 9 by 2. This is 0, 0. This is 0, 9 by 2. This is 0. Okay, this is B column. Now Cj, this minus this. So this is 0. 3 minus 9 by 2. 3 minus 9 by 2. So this is 6, that is minus 3 by 2. Minus 3 by 2. This is 0 minus 0 minus 9 by 2. So you see all Cj's are less than or equal to 0. So this is our optimal solution, and our optimal solution, what we get, x2 is still 0 and x1 is equal to 2. See, x1 is equal to 2 and x2 is 0. This is our optimal solution. And what is the value of this optimal maximum z? Z max. See, 9x1 plus 3x2. So 9x1, 9 into 2, 18. So this is our result. Z max is 18. Okay.